Thank you very much for the invitation. Thanks for coming here. Okay, so my topic is about equivariant Lagrangian correspondence. It's equivariant Lagrangian Floer theory. So it is based on mainly two works, joint work with Nai-Chung, Leung, and Li on equivariant correspondence, and my earlier paper with Siu Cheong Lau and Siu Cheong Lau on equivariant Lagrangian Floer theory. So we'll be thinking about this, and this would be the main picture of today, basically. So this is physical surface F1, and we are considering, for instance, an S1 action in this example on the physical surface S1, and then the moment map level would serve as a Lagrangian correspondence, and it is equivariant Lagrangian correspondence from the physical surface to the quotient CP1, the sphere. Right? And then the two main addition thing would be the disks bounded by the Lagrangian correspondence, the level, right? And the main thing is about this obstruction. That's the main interest. But before going to equivariant Lagrangian, so let me summarize the last talk, Lagrangian Floer theory, basically, using a principle, a classical principle of the Herford that, okay, so you consider connections on a compact smooth surface, let's say just 2 dimensions, let's say. Okay, and then, so this is an affine space, right? Space of all connections, just matrix one form, right? One form value matrix, so A is just matrix, one form value matrix, let's put it one form value matrix. Okay. Okay, so this is just an affine space, the infinite dimensional affine space, right? Okay. And then it has a natural pairing, just you wedge them together, right? Then you get a two-form value matrix. With X-rays, you get two form, because this is a surface, you can do integration, and then you get a number. So this is a function, this is a two form, right? This is a two form on this affine space, right? And then this is a symplectic two form. This is just a constant form, actually. This constant form on the connections, space of connections, sorry. And then another thing is you have gauge group action. You have a gauge group action on this affine space, right? Okay. And then the thing is that what the principle of them is that, okay, the curvature function, you have a natural function, right, of this familiar formula, dA plus A wedge A, turns out to be the moment map on this space under this gauge group action. Okay, so this is the principle. And for instance, you can take the surface to be our familiar torus SYZ picture. Okay. And then, so this is kind of like 1D field theory, and then, okay, and then we go to mirror symmetry, which is 2D topological field theory, meaning that we put this surface as a Lagrangian. Let's forget about the framing for a moment. Okay, just concern about this little sphere or the torus. Okay, so you put this surface as a Lagrangian surface inside a symplectic twofold now. All right, and then so the relation to SYZ is that we consider the connections to be the deformations of this Lagrangian, of this Lagrangian. All right. So for instance, if you just consider rank 1 connection, okay, then this would be just one form, right? If this matrix is just 1 by 1, this is just one form. If it is just one form, then curvature is just dA. If it's just one form, right? Then okay, so curvature equals to 0 just means that it's a closed one form. And then you model the gauge group would be just exact one form. So okay, so the space would be just holomorphic H1, which is the space of Lagrangian deformation up to Hamiltonian. Right? So for Lagrangian, if you have closed one form, you can turn it to symplectic deformation around it, right? and then exact one form return to Hamiltonian function, all right? So up to Hamiltonian perturbation, right? So this space would be the deformation space, right? Okay. So this is high rank analog, meaning that physicists usually think of this as brane, that you have k copies of the same Lagrangian stacked together. Okay, so that's why you consider high rank. All right, and then so now you have this space of deformations. Okay, you consider space of deformations is omega 1 LGL. One thing is that actually original work of Theobald is considering unitary connections, but for mirror symmetry purpose, we complexify the deformation space, and so we consider general linear deformations, general linear connections. Right? So this matrix value one form general linear. Okay. And then model the gauge group, complexify gauge group. So you can do the same thing here, right? So you can just consider connections, model the complexified gauge group. All right. Okay. Then this would be a holomorphic symplectic form, then, right? Because you complexify everything. Okay. So before it's just a real symplectic form, but if you complexify everything, this would be a holomorphic symplectic form. So it kind of saying that the moduli space of deformations naturally is a holomorphic symplectic space. Okay. And then so now this is our work could be kind of considered to be a generalization or extension of this statement that so because in SYZ torus may degenerate to singular fibers, and good singular fiber that we can consider would be like inverse Lagrangian, that we know how to do Floer theory. Okay, so we consider Lagrangian immersion like this. Okay, all right, and then for Lagrangian immersions, the deformation theory is defined by Ota Ono and Kaho Joyce. Okay, and then so there are many works to cite, so it's all written here. Okay, okay, and then we also have a localized mirror functor. So given such Lagrangian, we have a functor from the Bukai category of this symplectic manifold to the deformation space. But the important thing here is the following. So in Floer theory, we are not just considering the classical deformation space. So this is the classical deformation space that you consider connections. Because we have immersion, we also need to consider the branch jump between a branch jump and the immersed point, right? Okay, so it's in form of, also you can think of that as connection basically, right? So you need to describe the connection when you jump from one branch to the other. So that's why you have an extra component coming from the immersion. So basically this is the replacement of the formulation of a bond, right? You just add one more component describing the immersion, the jumping at the immersion. All right. So this is the classical deformation space. Right? This is the classical deformation space. Now, now in Floer theory, it's important to consider obstruction, which is M0. Okay. So M0 is counting of disks, mapping output to the Lagrangian. In our case, we just have degree 2, okay, in the degree 2, which are point classes in the Lagrangian immersion, Lagrangian, okay. So we count disks output to the Lagrangian like this, all right. And then we have corners, so that's why I draw it as a polygon. Now there are two kinds of deformations. One is A, which is the connections on the component. One is B, which is the corner, right, which is describing the branch jump. So B and A. Okay. All right. And then so actually you can consider the curvature function as classical part of this counting. All right. So BA, I write it here. So curvature function is BA plus A wedge A. So you can consider D to be our classical M1, which has one input and one output. Right. I draw it as a flow line, or you can think of this as a thin strip. Okay. And then you can consider wedge product as classical M2. So let me just write it as M1 usually beta 0, or let me just write it as constant. Okay, constant. If you just have smooth component, then M1 constant and M2 constant would be just D and wedge respectively. You just count constant disk. Constant disk. And that would give the wedge product if you use differential form model. Okay. All right. Okay. So that's why we call it the moduli space, because we consider the unobstructed deformations, weakly unobstructed in the sense that we allow identity. Okay, so this is, you can think of this as projectively flat instead of requiring flat connections. Okay, and then you model the gauge group. So it's very natural to consider. Okay, so let me point by point notice something.
That gets it so much.
Right, I don't want to make a lot of slides, so that's why.
It's just one slide.
Yeah. Well, more than one slide. Okay. So one thing to notice is, first of all, it is a stack, all right, in general, because this is a non-compact group, right? This is complexified gauge group, so quotient by non-compact group will give you a stack in general. And then, so you need to talk about stability condition to resolve it, or you conveniently use a quiver to encode the information. So that's why quiver algebra come up. That's the philosophical reason, because it encodes all the flat connections, all the connections in all ranks at the same time. So that's why we use quiver algebra. And the relation exactly come from this obstruction. Basically, classically, it is dA plus A wedge A curvature. Okay. Oops. I don't know what's going on. Maybe I just. Okay, I may need to restart then. Okay, I may need to just restart this program.
Oh wow.
Okay, it's okay. I will here. I don't know what's going on. Okay, let's pull it up. Okay, yeah. Okay, so all right, and then what replaces the this pairing, natural pairing, trace of wedge? Well, naturally, wedge is replaced by M2. Right? So the thing is that, as we have said, wedge product is just classical M2 and it becomes constant disk. But now the thing is that we have extra constant disk because of the immersion. If you just consider smooth Lagrangian, smooth surface, then okay, that's it. So wedge product is the classical M2. But because we have immersion, so M2 has more disks, right? So you need to also count constant polygons. So this is what I mean here. So you replace the wedge product by M2, then you have a natural holomorphic symplectic form. Right? And then this is skew symmetric because for constant disk we take perturbation such that it respect the involutive symmetry, so that when the output to this component, the answer is negative of output to the other component, so that this is a skew symmetric form. Okay, and then the slogan here is like, okay, it is exactly like a here box that, okay, so the floor theoretical obstruction M0, so this is quantum corrected curvature basically, is the complex moment map with respect to the gauge group action, and hence naturally the moduli space is holomorphic symplectic. Okay, so that would be the main thing. Okay.
That's special to a surface, or
Sorry.
the holomorphic symplectic structure on this kind of model.
Yeah, so holomorphic symplectic structure come from this one, holomorphic symplectic form. So this is just again, this is an affine space, and then this is complexified gauge group action on here, right? And
I'm asking if it's important that L is a surface.
Yes, right. Good question. So in high dimension, then you need to change it by wedging with omega to the power n-1 and so on, and also the intersection pattern would also be more complicated.
Yeah.
So I'm thinking about it, but
But you think it could still be holomorphic symplectic?
Well, when L is scalar. Okay, so now L is a Riemann surface, so we expect when L is scalar, this is still holomorphic symplectic, but okay, yeah, this is just expectation. So we are doing surface now. Okay. Okay, and then so actually our work is just focusing on framed nodal union of two spheres. Okay, so just like this picture. Okay, and framing that Drew has explained is out in basically with fixed trivialization essentially. Okay, so fix the gauge. Framing just means to fix the gauge essentially. Fix the deformation, fix the gauge. Okay, and then this would be a Nakashima-Kripke variety. Okay, so the moduli space would be a Nakashima-Kripke variety. Okay, and then if you have metric, okay, so let's say the Lagrangian is equipped with metric, and the bundle is also equipped with metric, then the deformation space is also equipped with metric, and then the mirror functor, right? You consider the Lagrangian intersection. All of these comes with metric. The branch sum is just homomorphism from vector bundle to vector bundle. If all of these have metric, then everything has metric, right? Yeah. And then so the monadic complex actually each term has a metric. Okay. And actually in ALE space, this is how ADHM and Oppenheimer, Nakajima produce Yang-Mills instantaneous. Okay, so this is a brief summary.
Sorry, so do you also have the moment map statement?
Moment map statement.
You do.
Yes. The moment map is the Floer theoretical crutch. Is the obstruction and zero. Okay, now we go to equivariant mirror symmetry, like equivariant Lagrangian Floer theory. All right. So this is our familiar picture that mirror symmetry interchanges symplectic geometry with complex geometry. One side is symplectic, and the other side I take it as an Ginsberg model. All right. So the familiar example is physical surface F1. There are four. This is toric, and there are four toric devices. Each toric device corresponds to a polynomial, and then this is so-called a Ginsberg model. In this case, it is just a function on C star squared. So this is a round polynomial. Okay. And then Teleman conjecture is about that when you have a Hamiltonian group action on the symplectic manifold. All right. So his conjecture is saying that okay, the Hamiltonian group action would correspond to a function on this mirror space. All right. So and the function, the base of the function, he described it as the Leung group of the Hamiltonian group. Okay. Model conjugation. And then there are two statements actually for Teleman's conjecture. So one statement is Hamiltonian group action is mirrored to this fibration. Another one is that the quotient, so this is the GIT quotient or symplectic quotient. Let's say symplectic quotient. The symplectic quotient is mirrored to a fiber of this fibration. So in this example, we see that quotient of the isogroup surface along this S1 direction would give you a P1. So that's the picture I had in the beginning. So this is the moment map, and then the quotient would be a P1. And then, so if you compare, so a fiber of the vibration, in this case, the vibration is simply given by Z. I forgot to write it here. So F is Z. This is F is Z. And then, so a fiber would be given by setting Z equals to constant. And the mirror of the quotient is just P1 mirror with just W plus something over W. P1, simple. Okay. So you see that actually there's some little bit discrepancy. It's almost the thing, but not exactly. And we want to understand why, what happened. Right. And the motivation of the motivation for Teleman is because of 3D mirror symmetry, we call it nowadays, okay? For pure gauge theory, so the space we consider actually can be considered to be a potential bundle of EG, all right? So we call that, okay, so given a group action, to consider equivariant cohomology, what you do is you consider the classifying space. So you consider a contractible space with free G action, so we call it EG. And then, so the aim is to make a free action on a space that is homotopic to X, right? So X originally may not admit a free G action, and so you multiply with a larger space which has free G action and contractible, then you kind of think of X quotient G, replace that by this one, and that is called XG, Borel construction, Borel space. So that is the XG. Right. Well, actually, to make it symplectic, it would be better to make everything symplectic. So instead, you do symplectic quotient, right? Make EG also symplectic by just taking potential bundle, and then make everything symplectic. That would be called XG. Okay. And then, all right, then it also have a natural vibration to T star EG, where you just project to this part, and that would be T star EG. So the space that Teleman considered would be like T star EG, or actually T star EG actually. So it's a hyperkähler quotient. So it's a stack point quotient by G, hyperkähler quotient. The point can be thought as T star EG. All right. So this is symplectic, right? T star EG is symplectic. You make one more T star to make it holomorphic symplectic. All right, so and then you quotient by G, so that would be kind of like T star EG. So this is the space you consider, and this is understood as a holomorphic Lagrangian brane inside here. So it's like SYZ principle that we consider torus and flat bundle over torus, but now it's 2D in 3D. So now, okay, the brane would be a holomorphic vibration over this holomorphic Lagrangian inside this holomorphic symplectic manifold. All right, so that's okay. And then
what do these three quotients? Is that just a static quotient, or what is it?
Hyperkähler quotient. Right. You fix some stability condition or fix some formal math level to define it. Right. Or if right written as bracket, then you can consider it as stack. Right.
But you still wanted some of a finite dimensional approximation, or how do you treat EG?
Yes, we do finite dimensional approximation, right. But yes, this is how we treat them. Yeah. Okay. And then he's okay. The 3D mirror, so-called, is so-called BFM space, which I basically think of that as potential bundle of this, but it's more than that definitely. But yeah, that's not today's topic. All right. And then this holomorphic vibration is considered to be holomorphic Lagrangian brane inside this BFM space. And so you see that, okay, 3D mirror symmetry in the brane level is in the situation here is exactly 2D mirror symmetry that you consider mirror of this vibration, right, of this Borel space basically, and then that would give you this, that should give you this vibration by Teleman's conjecture. Right. So 3D mirror symmetry is 2D mirror symmetry. That's the recent paper of Chen and Leung. In analog of 2D mirror symmetry is TDRT. That's why they name it this way, strange way. And then, okay, so this conjecture in closed string was now realized by Gonzalez, Mark, Pomiano. Earlier work would be Gonzalez, Tani, and more recent is Pomiano, Teleman. So the closed string construction is to do equivariant quantum cohomology for this symplectic manifold, and then you consider Seidel representation, Seidel action on this equivariant quantum cohomology, which is not my topic, so I just give you. right? For us, we care about the Lagrangian and its deformation space. Okay. So now we start with an equivariant Lagrangian now. Okay, so L is now G equivariant. Okay, so this is the earlier picture I had. So I just want to explain that. Okay, so the superpotential come from counting disks. So you see that these terms actually are corresponding to disks, mass of two disks, okay, bounded by a SYZ fiber, Lagrangian torus fiber. Right. Here I just make it simple. I choose the area to be like this, or A, so that I just don't want too many parameters. Okay. And then now we go to G equivariant Floer theory. Okay. So the aim is to construct a fibration like in Teleman's conjecture. All right. So first of all, we consider the deformation space of Lagrangian like before. All right. Now the question is how we cook up this fibration. Right? Why do we have this fibration? And then what we did with Kim and Jen, okay, what we did was that we consider the Borel construction. We do Borel construction for everything, okay, and we do finite dimensional approximation. Right? So we define Floer theory for LG inside XG using the finite dimensional approximation using Morse model actually we use. Okay. Okay, so this is equivariant Floer theory. Okay. Now the additional thing is the following. So the obstruction, now for the Borel space, there's extra degree 2 generators. Okay, so because this is in the Borel space, there are equivariant parameters. For instance, for torus, the equivariant parameters would have degree 2. So then you have an extra component for the equivariant Floer theory. And then we use this extra component to be this fibration. So you have a natural fibration over H2BG. Okay, so basically it just means the equivariant Floer theory admits a natural module structure over BG. So you have a module structure over cohomology of BG, and so that's why you have a vibration over H2BG. And it's that degree 2 because M0 here, the obstruction is of degree 2, just like the curvature. The curvature is a degree 2 form, right? So naturally this is a degree 2 element, so that's why this is going to H2. Okay, and then for torus, actually, it's pretty simple. For torus, and when the group action is just S1, all right? And assuming that the torus does not have mass of 0 disks, okay, then the equivariant, okay, this equivariant obstruction, I call it the equivariant obstruction, H, okay? So this is just of the form log Z, where Z is the flat connection over the torus. More precisely, actually, I use boundary deformations, but I think, yeah, anyway, so actually, this is boundary deformation, and we consider exponential of this actually to be the flat connection. But anyway, yeah, so that's some technical point. Okay. Okay, so this is one thing. Now we have a vibration. So this vibration is actually kind of like localized version of Teleman's conjecture. All right. So first of all, the mirror is in the localized sense because we are looking at one Lagrangian, and later on we want to glue them together. We are looking at one Lagrangian, so this is in the sense of localized mirror. And here the vibration is also in the localized sense. So it's going to H2 of BG. Okay, and then now we consider the quotient. We want to compare with the quotient, right? So Teleman's conjecture have two things. One is the vibration. One is about the quotient. Okay. So first of all, so the equivariant Lagrangian naturally has a functor, localized mirror functor, that constructed with Conan and Hensel, that it goes to the unobstructed moduli space of the equivariant Lagrangian. The unobstructed moduli space is now also, you need to also require the equivariant obstruction to vanish. All right, so that's why you need to consider fiber of this fibration. You require the equivariant obstruction to vanish. Right? Okay, so naturally, the Moore-Cartan space, the deformation space of the Borel Lagrangian LG is a fiber, is the fiber at zero of this vibration. Okay, so this is very natural. Okay, you have a localized Muir counter there. Okay, all right. Now, okay, and so setting log z to 0, meaning that we set z equals to 1. Setting z equals to 1, we have this potential. Now we have the discrepancy still, right? Okay, so the disk potential for LG after setting log z equals to 0, after killing this equivariant obstruction, is this one. Is right? Is this one, which is not exactly the disk potential of the quotient. And then we need to explain this discrepancy. All right. Okay. So in perfect case, so if we do not have discrepancy, then we would expect that there is a equivariant Lagrangian correspondence, all right, which is given by the moment map, all right. So the moment map level, in this picture, this is toric picture. So this moment map level is actually like this. Okay, so P1 cross S1. So this would be the moment map level. The moment map level can also be regarded as a submanifold, Lagrangian submanifold, inside the product of the upstairs with the downstairs. Right? So this is product of upstairs and downstairs. Okay, and this is naturally a Lagrangian inside there. Right? So the moment map level. Notice that we take G. So philosophically, it is that xg is homotopic to the quotient, right? xg is homotopic to the quotient. So basically, xg is homotopic to x bar, and this is just x bar cross x bar homotopically. And so the moment map level correspondence is nothing but it's homotopic to the diagonal. Right? It is just the diagonal of x bar cross x bar. Basically, it's homotopic to that. All right. Okay. All right. So in perfect case, in nice case, then we should have this equivariant Lagrangian correspondence by earlier work of Graham Woodward and also Fukayas, who constructed correspondence trimodule for the correspondence. All right. Okay. So in perfect case, we should have this, right? And then in good case, then the Morgei space would get identified using this Lagrangian correspondence. All right. So everything would match. But you see that there's a mismatch. Okay. And then it turns out the mismatch is exactly corresponding to the reason for the mismatch is that the Lagrangian correspondence is obstructed. Right? So the Lagrangian correspondence turns out in such simple case, like isogroup surface, even in such very, very simple case, it turns out it still has non-trivial obstruction. Sorry. All right. And then this non-trivial obstruction, as you see, so exactly corresponding to these two terms. So one is an easier obstruction, which is this one. This one corresponds to this green disk. This green disk actually moves freely. Okay, this green disk. I'm trying to draw here. This green disk corresponds to here. Is moving freely. Okay, so it varies to the unit, to the fundamental class, basically, of the moment map level Lagrangian. Right? So that's the green disk contribution, and it contributes to the disk potential, which is this one. Now the obstruction term is this one. This red disk actually has Maslow index 0. Right? You can actually see from the direction around this fixed point. Okay, from the direction of this fixed point. Okay, you compute the pairing with the disk direction. You find that actually it has Maslow 0, and actually you can also see that because F1, this P1 has Chern number 1. So Chern number is 1. And Maslow index is 2 times that. And so it should add up to 2 then, because the Chern number is 1. Right? And so these two disks, the Maslow index should add up to 2. So this one has the green disk has Maslow index 2, and the red disk has mass of index 0, and that would contribute to obstruction of, so that means degree 2 term of the M0, the curvature, the degree 2 term of M0 of the Lagrangian correspondence. It has non-trivial obstruction. And so indeed we need to do bulk deformation to remove the obstruction. All right, so you can, because it's lives in the product, so the Lagrangian correspondence lives in the product, you can either do deformation on xg or on x bar. You choose, you make your choice. All right, they are homotopy to each other anyway. All right, so okay, so after doing the bulk deformation, so the bulk deformation in this case it is just on the P1. The bulk deformation is now just on P1. For instance, if you do the bulk deformation downstairs, right? So bulk deformation means that you count disk with interior insertions required to be mapped to the cycle you choose, the chain you choose. All right, and this insertion is all possibilities of numbers of insertions. All right, out. So this disk, okay. So if you consider bulk deformation by this point class, let's say the north pole of P1, basically you can think of that as symplectic deformation. Okay, it's basically the effect is changing the symplectic area by divisor x, changing the symplectic area of this disk. And so if you change the symplectic area, then that would change the 1 over
Can
W.
you say that again? It changes the symplectic structure in which way?
Basically, if you
Effect.
do bulk deformation on the north pole, then it is changing the symplectic structure by increasing the area of the disk passing through north pole.
So that's not a no.
Yeah. And then it would change this one downstairs. So this is the one for P1. It would change this 1 over W term to something else over W. Okay, that would match with this. So you change this symplectic area.
So then the Lagrangian in the middle, the two pieces become equal.
Yes. So right. So one is W and the other one is something over W. So the south pole disk, the south disk would be still W, but the north disk would be like this. Yeah. Because you do bulk deformation only on the north pole. That's the obstruction. That's the obstruction value. Okay, so let's formalize the statement. Okay. All right. So let's say in good case, okay, it's already weakly unobstructed. So actually in our current work we will, do bulk deformation to make it weakly unobstructed using curve one subjectivity. But anyway, now in our paper we assume this is weakly unobstructed. Okay. So if it is weakly unobstructed, all right, then you do have the Lagrangian correspondence, okay, between LG and L bar. Right? LG is the Borel space, which is homotopic to the quotient. Okay. If the correspondence is weakly unobstructed, then there are three statements. So there are three things. First is the Mercaton space. So let me draw conceptually here. So this is the moduli space of deformation, the Mercaton space. I call it localized. Okay. And then you also have the tangent space, which is the Floer cohomology. If this Mercaton space is universal, right, then Floer cohomology would be the tangent space of the Mercaton space. All right. And then now we are in weakly unobstructed situation. We also have a Ginsberg potential, is potential. Okay, so that's why there are three things. Okay, the statement would be that the Lagrangian correspondence would identify all these three things, right? Okay, so let's look at the picture here. Okay, so first of all, you have the moduli space, localized moduli space upstairs. Okay, this is for L upstairs. And then you have the equivariant obstruction if you consider Borel space. So that's how you get this fibration. And then you require the equivariant obstruction to vanish okay, then that would correspond to the Morgei space of the Borel space. Then, right? The Borel LG has obstruction containing this term. That's why you require it to be zero. You require this obstruction to be zero. Okay, so that would be a fiber of this. And then the correspondence would identify this fiber to the Morgei space downstairs. So that would be a statement. And then this potential also got identified up to a correction of the correspondence this potential. All right, and then the flow homology would also be get identified. So this is going to this example again. Okay. All right, so this is our previous example. So actually, I have already explained. So here I just summarize. Okay. So this potential upstairs for the torus inside the His group surface has 4 terms. Right? And then the correspondence, the Lagrangian correspondence, has 1 term, which is the green disk, which is this one. Okay. Well, it has a negative sign because actually the product on one side is negative omega. So recall that we have this product, xg cross x bar. This is the quotient. This is the Borel space. The Borel space is just homotopy to the quotient. And then on here, actually, we use negative omega. And on here, we use usual omega. So to make the basically like the diagonal to be Lagrangian, to make the correspondence, to make the moment map level to be Lagrangian. Okay, so that's why we have a negative sign here. Okay. And then, okay, so after bulk deformation, then the P1 potential will change. Okay, and the theorem is saying that they must match, they have to match, and so yeah, if you Q the obstruction, then it has to be like this. It has to match. All right, and then okay, so the equivariant Lagrangian Floer theory. I'm talking about the construction using Borel construction, okay, pioneered by Seidel Smith. They considered Borel construction for C2, actually. Okay. There are other constructions by Woodward Xu. So they use a gauge Floer theory, which is using gauge equation, is different type. And then Daimi Fukaya and Xiao assumes construct equivariant transversality, right? Instead of doing it on the Borel space. So for us, we use Borel construction. The advantage would be okay. So first of all, of course, it singularized L quotient G, right? So even when L quotient G is singular, you can still define equivariant Lagrangian Floer theory, right? Because you desingularize it. Okay. And then another thing is that you have module structure if you use Borel construction. So this is advantage of Borel construction in general, right? Borel did this for these 2 purposes. Exactly. Okay. All right, so let's talk about ingredients of proof. Okay. All right. Okay. Okay, so this is our statement. I just copied here the same thing. Okay. Now the key ingredients of proof well, is the equivariant Lagrangian correspondence. Okay, so earlier theory, the theory would be Woodward. They considered composition of correspondences, and more recent work is by Fukaya. He constructed A-infinity primordials. So these are the important theories for Lagrangian correspondence. Now, we basically leave everything to Borel space, all right? And then the key role is played by basically this so-called cyclic element, this fundamental class, or in the Dirac model, this is the constant function 1. Okay, so here I'm simplifying to bimodule basically now. Okay, so to make a simplification. Okay, so the space we consider now is this product xg cross x bar. Right? So the Borel space and the quotient. Okay, so basically LG. Okay, the Lagrangian correspondence is like a diagonal inside here, essentially, the map level. Okay, and then there is another thing which is the product LG cross L bar. Right? Okay, so upstairs and downstairs, Lagrangians, product them together, you also get a Lagrangian inside here. So this is a comparison between this Lagrangian and this Lagrangian. Right? And then these two Lagrangian intersect exactly just on LG itself. So the picture is this one. All right. Okay. Right. This is the picture actually. So let me draw it again. So this is the moment map level L pi, right? And then the intersection of L pi with L cross L bar in the product is exactly just L itself. So this is L. Right? I'm drawing the torus as I'm just drawing the base point to represent the torus. All right. So L pi intersect with LG just on L anyway. Right. So the intersection of these two would be exactly LG actually. Okay. And then this one is the constant function one inside the intersection. Inside the intersection. Inside this product space HG cross this bar. Right. So we are considering Lagrangian Floer theory between these two Lagrangians, basically. So CF these two. So intersections between these two. This is clean intersection. Okay, so the intersection is intersecting along LG. Okay, and then okay, so this is the key element one. Okay, so first of all, you want it to be this is a cocycle condition. You want it to be a cocycle. Right? You want D of it to be zero. Right? So you want it to be closed under differentiation. Okay. Right. First of all, you solve. Actually, you for each B bar you solve B so that this is closed. Right? So this is actually computation over Novikov ring. Right? So solving order by order, basically. Right? And then second is that, okay, so you have this A infinity equation. So this is the first one of the A infinity equation. M1 squared is 0 up to M0, right? M1 squared is 0 up to M0. So these W, this potential, and this equivariant obstruction are all M0, basically. Okay, so M squared equals to M0, basically. M1 squared equals to M0. And then you apply this to this cyclic element, this one, this constant function one. Okay, then you would get that this equals to 0 because you solved it already. This equals to 0, and then W would satisfy the equation written here. Right. Okay, so this equals to 0, and H also equals to 0. H is the equivariant obstruction. Okay. Okay. And then finally, you use M2. Okay, so you consider M2 with this cyclic element. All right. So what you do is, okay, so let's say you have an element inside L bar, you pull it back to this product. If you have an element inside L bar, you pull it back to the product and consider M2 with the cyclic element. So M2 is counting disk. M2 is, so basically the picture like this. So this is in, this is out. You just have one more element on either this, on this side, LG. So this is the side of LG cross L bar. So if you have an element, inside LG, you pull it back to the product and then insert it, right? Take the M2 and you have an output. Okay, so you go to this LG cross, go to here, right? Go to here. Okay, here. All right. Similarly, if you have an element inside LG, you do the same thing. Okay, and then because classically they already match, and then it's over Novikov ring, you extend the isomorphism. Okay, so that's why you have this isomorphism. All right, so that's a brief description of the two ingredients. Okay. Okay. right? And then now, how do we compute the equivariant obstruction? In general, it would be pretty hard. If there are mass of zero contribution, the equivariant obstruction would be pretty hard to compute. Okay. Now, in toric case, in toric semifinal net case, then we can actually it is given by the inverse mirror map. Okay, so let's illustrate by this example. Now, to get non-trivial mirror map, non-trivial mass of zero contribution, okay, let's go to Hirzebruch surface F2. Okay, so this is Hirzebruch surface F2. We consider this to be toric quotient, meaning that this is quotient from Cn, now C4 by T2. Hirzebruch surface is quotient of C4 by C2, well, by T2. Well, I cannot draw C4, so I draw C3. I can just draw C3 here. I cannot even draw C3 without 3. But okay, so all right. So this is C4 quotient along these two directions. All right, and then each quotient direction corresponds to an S1 direction, right? So the S1 action gives a equivariant dispotential. Okay, and okay. So let's consider this direction. 0, 1, 1, 0. Okay, 0, 1, 1, 0 just means I'm labeling the divisor.
I think that's very difficult to see for a lot of people.
Okay. Yes.
Maybe you can erase them. Yes.
Okay. Yeah. I can erase something. Thank you. Okay, I'm labeling the divisor. This is step 2. I'm labeling the divisor as 1, 2, 3, 4. So this is position 1, position 2, position 3, position 4. And then so 0, 1, 1, 0 means these 0, 1, 1, 0. Okay, sorry for that. Maybe I switch. I'm not. Maybe I wrote it wrongly here, but let's point this way. Okay, basically this direction and this direction. That's what I want to say. Okay, all right. Okay, and then okay, so the equivariant dispotential for the torus upstairs would be easy. All right, would be just log Z2 Z3. Okay, for the upstairs torus. So you consider the Lagrangian torus upstairs in this F2. The equivariant dispotential along this direction is easy. The circle direction is just log Z, just log of this. Now the thing is that the Lagrangian correspondence, the moment map level has a non-trivial equivariant dispotential, equivariant obstruction. Right? Okay, so you want to find it out. You want to find this out. Okay. Now the theorem is telling you that okay, so this has to add up to 0. You take this fiber in order to match upstairs and downstairs. You have to make this to be 0. So this whole thing has to be 0. So then this is how you find out the dispotential obstruction of the Lagrangian correspondence. So and this term actually corresponds to this is a disk, although this looks like a sphere. Okay, so this is a sphere in F2, but for the Lagrangian correspondence, you can consider this sphere as exactly match that picture. Okay, so you can consider this sphere as split into 2 parts. One is this one, and one is this one. So actually, this sphere is considered to be a disk inside the Lagrangian correspondence, like this. And this is how this Q come up. And of course, if you you take a series expansion of log, right? Then you have Q squared and so on, because it is mass of 0. So it multiple of it is still mass of 0. So it still contributes.
How do we know that the coefficient is that? The coefficient is always 1.
Which one?
I mean the expansion of operator 1 plus q. My the mass of the tensor is already
So this expansion is just like Q and minus Q.
it's right. So the coefficient of is always 1 up to
Wait. 1 over 2, 1 over 3, and so
Oh
on.
yeah, sorry. Yeah.
And we are not finding them directly. We are finding them through this equation.
Yeah.
And that's actually because of the earlier work of our early work that we know that this potential of visible surface F2 is 1 plus Q here. So it has contribution like this. This is contribution of 1 plus Q. And then the takeaway here is that the equivariant obstruction for toric quotient would be log of the 1 plus Q. Right, so finally, a final slide. Okay, so we talked about Hilbert surface F1 because actually that would be a baby case, a first case of so-called Seidel representation. So here, Seidel representation is that you take a symplectic manifold. I changed the symbol to Z, not to be confused with earlier. So okay, so if you have a symplectic manifold, let's say you have a Hamiltonian S1 action. It's more general actually the setting, but let's say let's make the setting to be simple. Hamiltonian S1 action on the symplectic manifold Z. All right. Then you can hook up a one high dimensional space. All right. Okay, which is given by this symplectic quotient. You just cross C2 quotient by S1. So you make a one higher dimensional space. All right. Generally, you think of that as two copies glued together. Actually, you think of this space as this glued with this. Okay, so this is Z cross P1. Sorry, Z cross C. Z cross C. Okay, so let me draw this way. This side is Z. This side is Z. And this is, let's say, C. This is another copy of C. Actually, it's Q. Let's just C. Z cross a disk, Z cross a disk, and then you glue them together. More generally. Okay. Okay, so you have this Seidel space E. All right. So why he considered this is because this will give you an action on the quantum homology of Z of the symplectic space Z. Z is now regarded as the fiber, right? As the fiber direction, vertical direction. Okay, so what he did is that you count section. Okay, you count section like this. You count section. Okay, from one fiber, let's say fiber at infinity over P1, right, to the fiber at 0 over P1. Okay, you count section. All right, the counting of section. Actually, this looks complicated. It just means evaluation of the counting of section at the output mark point to Z. So just taking output to Z. Okay, right. So that would give you an element. That would give you an element inside the homology, and you regard this as quantum homology. Okay, it turns out this element is invertible. Right, so this operation will be invertible. Okay, and then so multiplication by S define an action on the quantum homology. And this is very important for shift operator theory and so on. Preparing quantum homology. Right? And okay, so basically we want to do the same like in Hilbert surface F1. Okay, this is for F1, right? For the example of F1. In that case, Z is just P1. Okay, Z is just P1 in that case. Okay, so what we want to say is that the correspondence between this Seidel space and Z itself, the correspondence has obstruction, right? This correspondence has obstruction. just like F1. It has obstruction. Okay. However, in this case, in this nice scenario, the obstruction, we want to say that it can be computed. Okay. So we want to say that actually that is basically given by the Seidel element. Right. So okay, so this is a work in progress. We want to mimic the case of F1 to move to Seidel space. All right. So we want to say that the obstruction of the correspondence is exactly the pre-image of the Seidel element. The Seidel element is inside C, and you have a quotient map from the correspondence to the quotient. So this is the pi. Okay, you pull back Seidel elements from the downstairs to L pi. We want to say that this is the obstruction, and the reason for this is because of degeneration. Okay, so well, here I think I draw degeneration like moving this monomap level fiber to the left-hand side. Okay, so for instance, in this simple example of F1, this would be the degeneration of P1 times S1 to P1. Right? The circle direction shrink, okay, to a point, so you get P1 in that example. Okay, or you could think of that as degeneration right at here. Okay, so then it degenerates into two copies, the toric degeneration, but well, Z may not be toric in general, of course. So I draw it like toric, but in general Z is not toric. Okay, but it could also degenerate into two pieces. This is the picture. Okay, so you degenerate it, then the disk becomes sphere. Okay. So what we want to do is we want to construct a cobordism, okay, from the open disk to the closed sphere. Okay, we want to make this cobordism, so to argue that the obstruction is exactly given by the Seidel element section, the counting of the section. Okay, then if it's true, then we know how to, because we know the obstruction, then we know how to do bulk deformation. We just exactly bulk deformed by the Seidel element, so the Seidel elements would solve the obstruction then. Just exactly like the example of F1, bulk deformation. Right? And then by doing this, because bulk deformation, the first order is the closed open map, then we know the closed open map of image of the Seidel elements would be basically the holonomy of the S1 action. Okay? So that would be encoded as the exponential of the equivariant disk potential. Recall that in simple example, HL is just log Z, so this will be just Z, basically, the holonomy of the S1 direction. Okay. All right, okay, let me end my talk.